COVID-19 studio. So week three advanced hydronics. As normal, we got Jim DePalmas here doing the questions. Chris and Eric are in the back running the cameras. If there's any questions from last week, just put their work in here this morning. There we go. All right, now we're too fast on it. Okay, so Jim will be handling questions again on that right-hand side of your screen. You got your drop-down menu. You got your handouts. We're going to be looking at pages 44, 48, 50, and 52 today. Those are the pages that we're going to be utilizing. If you have questions in that right-hand column, go under questions, type in your question. Jim will be there answering questions. Today is going to be, we're going to run through a few things this morning, right now, and then we're going to get into root cause troubleshooting. When we get into the root cause troubleshooting, it's going to be basically, we're taking the course and putting it in your lap. We're going to put you in a boiler room and you're going to do the calculations, and it's going to be interactive. So find that question bar, chat bar, whichever one you want to use. Find one of those, because we are going to be relying on the audience for a lot of the answers. So if anyone has any questions from session 2 last week, when Jim did the floor plan design, you can send those in. For today, we're gonna come right out of the gate looking at static pressure. What is static pressure in the system? How does it work? What does it do? And so on. The location of a circulator. So here we have the circulator on the supply, zone valves on the return. On this system here, we have the circulators on the supply, and that's a circulator system, no zone valves on the return. We're going to take the myth out of primary, secondary. We want to simplify primary, secondary piping and just make it as easy as possible for everyone out there. We're going to take a look at what is the best system for your application. Is it a zone valve job with one circulator, or is it a system with multiple circulators? And there's really no right or wrong answer there. This debate has been going on forever, circulator or zone valve. But we're going to put some numbers to it and let you decide how you want to go. Then it's root cause troubleshooting. We're going to lay a problem out in front of you, and based on what you've learned in week 1, week 2, and today, you're going to start to figure out some basic hydronic stuff that's in a basement, and we're going to elevate you to really be able to figure out exactly what's going on, dive down, get all the way to the root cause of the problem. So, Jim, we're good? All right, we're going to go static pressure. So here on the screen, you can see, we got a 5-story building on the right, we got a 1-story building on the left. We get phone calls all the time, and people want help sizing a circulator. And sometimes the first thing they say to us is, it's a 3-story building. I never hear, oh, I need help sizing a circulator, it's a 1-story building. So the myth is out there that the height of the building, so this is that 5-story building on the right-hand side, right? So if my boiler room is right here, and Jim said last week about total equivalent length, right? We would measure the heat circuit up to the top of the building, over, down, and back to the boiler. We would take that number, multiply it by 1.5, then 0.04. That would tell us the head loss of that heat circuit. So the confusion comes in, this is a 5-story building, that heat circuit, let's call it 300 feet. If I take this and make it a 1-story building, and my boiler room is still here, that pipe distance is still the same, that circulator size does not change. So static pressure does not affect the size of your circulator. Static pressure is going to be geared towards what's going on within the system from a pressure standpoint, the water within the system, the pressure reducing valve coming into the system, and we'll get into that. So here, if we were to do the math on this system, it would be based on the total equivalent length around that building and that would get us to the point where we would have a 0034E on this job. And both the 5-story building and the 1-story building would have the same circulator based on the amount of pipe connected to the heat circuit. Okay, that's what's going to dictate the size of the circulator, not necessarily the height of the building. So with that being said, static pressure refers to the weight of water in a system. Static pressure does not affect pump capacity, feet of head. So really that's the synopsis here. Does not affect it. 1 PSI elevates water in the system 2.3 feet or about 28 inches. So what we're doing is we have this pressure reducing valve here at the boiler. And we take street pressure, put it through the pressure reducing valve. They normally come out of the box at 12 PSI. Our expansion tank also comes out of the box at 12 PSI. And right under here is a Schrader valve. So this bottom portion is filled with air. And we're looking at about 12 PSI. Feed valve takes street pressure, reduces it to 12 PSI. So we have 12 PSI on the top of this rubber diaphragm in here, and we have 12 PSI of air on the bottom side. So we fill the system, it's a 12 PSI system, everything is good. We take and fire up the boiler, we start to heat the water. Our expansion tank is here, we heat the water, it expands, it'll push down on the rubber diaphragm a little bit, and then you'll heat your home. The boiler will start to cool down, the air pressure will push back up because the water has now shrunk again, and this is how the diaphragm works, goes up and down, right? So think of this as a Ferris wheel within your boiler system, right? The height is strictly going to be geared upon my system working pressure. Pressure coming in, pressure in my expansion tank. If you're ever at the amusement park and you look at a Ferris wheel, you would think the motor on a Ferris wheel would be, huge, but it's really not that big, because if I have a chair up here at the top, I have a chair here at the bottom. As I start to move that Ferris wheel, this weight's coming down as I'm lifting this weight up. Same thing happens in a hydronic system. You can see here in our diagram, if I'm water up here in this highest circuit, and I turn on this circulator, and this just creates a pressure differential from the front side to the back side. This water up here is now going to start moving this way, coming down from the highest floor back down to the boiler. At the same time that's happening, the equal weight of water is being elevated upwards to that heat circuit. So think of that's what we're talking about when we get into static pressure on a hydronic system. So we buy these components, and I already said this comes out of the box, should come out of the box at 12 PSI. Your feed valve, pressure reducing valve, comes out at 12 PSI. Why 12 PSI, right? That's always the question. So back to that, 1 PSI is equal to 2.31 feet of head pressure. So 12 PSI times 2.31 is 27.72. So that means we have the ability to elevate water from the lowest point in our boiler to the highest point in the house, 27.72 feet from the boiler to the highest point with our standard 12 PSI expansion tank and our standard 12 PSI feed valve. So realistically, if we always want to keep 4 PSI on the top, the highest point in our system, to make sure that we can move air bubbles, that means about 18.5 feet of height. And if you want a shortcut to figure that out, if you're not going to remember that 1 PSI equals 2.31 feet, if you just take 0.43, use that as your multiplier. So 18.5 feet times 0.43, that's 7.95. Add 4 to that, basically you're at 12, right? So that'll get you have 18.5 feet from the boiler to the highest point in your system. That usually equals about a 2-story house. That's where the 12 PSI came from. That's why your expansion tank comes shipped with 12 PSI of air in the bottom. That's why your feed valve comes out of the box at 12 PSI. So again, we want you to know where these numbers come from. Now you know where they come from. But let's say I have a system that needs more than 12 PSI because I'm greater than 18.5 feet from the lowest point in my boiler to the highest point in the system. So I have to make a change. So what do I have to do to make that change? So I'll take and just move this rubber diaphragm down, and let's say that's approximately where the rubber diaphragm would be in a normal 12 PSI system. So now I have to elevate the pressure in the system to 16 PSI. The only correct way to do this is the expansion tank would be off the system. I would go down here to the air Schrader valve, and I would put in an additional 4 PSI to get 16 pounds of air on the bottom. Then I would go to my feed valve, and I would make the adjustment on my feed valve, put 16 PSI of water on the incoming water side. And that would allow the expansion tank to still remain in the proper position. So what that'll do for us is that's going to allow the expansion tank to live in a comfortable position. It will allow it to expand and contract as water heats up and cools down within a heating system. That's how it's done. If you want the expansion tank to live its full life, that's how you would do it. A lot of times what we run into in the field is guys will take and put an air gauge on here and think they're reading just the air side of the expansion tank, when in reality is they're reading pressure of the system. So it's very difficult. You cannot get a proper air reading on the bottom of this tank without removing it from the system. So let's go back to that 18 PSI system. I want to have an 18 PSI system, but I never adjusted my air side. What would happen? What would it look like? Because we normally don't get to see inside of an expansion tank. We have a cutaway here, so it makes it nice. I go to my feed valve and I just elevate this to 18 PSI, and I push the button and it's going to feed to 18 PSI. When it does that, it takes this rubber diaphragm, because the 18 PSI is greater than the 12. I've now expanded and stretched my rubber diaphragm down like this. So now I'm going to heat the water up in the system, and I need to expand that water. The water's going to expand. It just happens when we heat it up. Now I'm going to start to push down this rubber diaphragm, and you can see here I'm going to start to stress that because the pressure on the top side is greater than the pressure on the bottom side, and the rubber diaphragm is going to take all the abuse. And this tank will probably fail prematurely because I don't have equal pressures on the top and bottom. And this goes the same for a domestic hot water expansion tank. You're putting one on a 40-gallon direct fired water heater. You need to set your incoming pressure and your air pressure to be close to the same, so that when we expand the water in the tank, it has somewhere to push back into the system. Okay, so that's what will happen. That's what will cause us to fail prematurely. We have to have equal pressures, system pressure and air pressure on this expansion tank to allow this diaphragm to do its job properly. We good on that, Jim?
Absolutely.
Okay. So we'll keep going. So here we basically, we're looking at static pressure, what's effective, where do we go to? We go right here. This is the point of no pressure drop. So this is very important to us right here. This is what we're going to look at. We're going to look at the expansion tank. We're going to look at where the feed valve or the air separator is, and where our boiler pressure reducing valve comes in. And there's your components. That's a breakout of your components. That's what you're going to look at. That's where we're going to see exactly what's going on here at the point of no pressure drop. Because we never want our circulator to pump into our expansion tank, because we'll take the positive pressure that's created on here, will actually pull the positive pressure from the backside. So it'll almost be a negative. Okay, so again, this is just a quick little showing of what it looks like coming out of the box. The rubber diaphragm will be pushed all the way up because we have air pressure here pushing against it. As we add the feed valve, we turn the water on to the boiler system. It'll push this little rubber diaphragm down a little bit and we'll equal out. And then as we start to heat the system up, it will expand down. As the water expands, it'll push down on the rubber diaphragm. That's what's going on inside of a typical diaphragm style expansion tank on a system. So hopefully, if there's any myths out there, we cleared it up. Jim's giving me a thumbs up, so there must be a lot of questions flying in. I do hear him over there typing away, which is good. So this is just a quick, you want to take a snapshot of this. This just breaks it down based on feet of elevation from your lowest point in your boiler to the highest point in your system. You'll multiply that by 0.43, and then you're always going to add 4 psi to that number. That way, if there's any air on the highest level, you're not going to have an air party up there and create a service fault. So that's what you would do in a system. Keep this handy. Just keep this in mind. This could be on root cause troubleshooting, whether it's this week or next week. Be alert. So I talked about circulators not pumping into an expansion tank. A circulator system, a zone valve system. Is the location of a circulator important in a hydronic system? The answer is yes. Pump towards an expansion tank, there's the question. And the reason this is a question is because you go back several years ago, a lot of boilers came with a circulator, and the circulators were mounted directly to the boiler. And they were mounted on a return pipe going into the boiler. The reason they were there, that was a packaging thing. It was much easier to package a circulator, holding it directly onto a metal header, and it was on the return. It just worked. So this circulator location, the pumping away theory, that is all, you read Dan Hollihan's books, and a lot of it has to do with saying, I lost remote. There we go. So when we turn this circulator on, we have to have the ability to create a pressure differential from the inlet side to the outlet side. And in our world, we always want to create the pressure differential so the positive is on the outlet side of the circulator. The reason we want that is because we need the positive side of the circulator to push against our heat circuits, the friction within a system, the resistance within a system. So we never want to take and pump directly into the expansion tank. If I put the circulator on a return, my positive pressure would make it to here. It would come into the expansion tank, and I would lose it right there in the expansion tank. And I would not have the positive pressure to push against my heat circuits, which is the resistance in the system. That's where my head pressure comes from, is the length of this heat circuit. So what can we do here? We're going to give you an example of what this would look like now. Just to keep this diagram clean, we did not put the boiler and everything else in there. We're just giving you circulator location. This would be a typical heat circuit. So the circulator is off. There's no differential. We have a expansion tank with 12 psi, which means we have 12 psi on the right side of the circulator, 12 psi on the left side of the circulator. We're going to lose 8 psi going to the upper level. That's 18.5 feet. We're going to lose 8 psi going up to the highest level in the home, which leaves us 4 psi at the top of the heat circuit, which is what we really need to maintain. So this is pumping into the expansion tank. So let's take a look at this in real world scenario. You're in a basement. This is the system you're looking at. What takes place? So when that circulator comes on, we're still going to have 12 psi on the front side of the circulator. We're still going to lose that 8 psi going up the hill. Our circulator did create the 4 psi differential. The problem here is it's going to happen on the backside because we're pumping into an expansion tank. So we took 4 psi from the backside. Remember, that was at 12. Now it's at 8. Our front side, where we want the positive pressure, stays the same at 12 because we're pumping into the expansion tank, which means that we will have 0 pressure at our highest point in that heating system. that means that we have a potential to start stacking air bubbles on that highest level in the house and creating a no heat situation, because we're going to have air bubbles stacked there. We're going to be unable to move the air pockets, and you're going to end up with a no heat coil going out there purging the system. So what is the solution? I can't give you a problem without giving you some type of a solution. If you have the ability to elevate the pressure within the system a little bit to try to maintain some pressure up at that highest point, that may work. If that does not work, adding an air can up there in that top corner is also not the answer. And we see this a lot when we go out on jobs is, you know, this was the problem. They keep having an air problem on that third floor, second floor, whatever it is. So we'll go put an automatic air vent there. And every time we get to 0 PSI, we actually have the ability to suck air in through that automatic air vent. That needs pressure up against it, so it won't allow air to enter the system. So in this scenario, really, we either have to try to elevate the pressure, keep some 1 or 2 PSI at that highest level, or we have to possibly think about moving the circulator. And that's not always the easiest because of the piping. But here, where we're pumping away from the tank, here's our tank, here's our circulator, we're pumping away from the tank. Okay, that point of no pressure drop, same exact system, same scenario. We're going to 0 PSI, no differential because the circulator's off, 12 PSI in our expansion tank, 12 PSI on the right side of our circulator, 12 PSI on the left side of our circulator. We're still going to lose that 8 PSI going up the hill, which sitting still right now, no demand, 4 PSI at the highest point. I'm going to turn the circulator on. The circulator does create my 4 PSI differential, but in this scenario now, my positive side, which is where I want my pressure to be elevated, goes to 16. There's my 4 PSI differential. The backside will stay the same. Point of no pressure drop. So I have backside of my circulator, no pressure drop. All my circulator's ability, my +4, is coming out the positive side to go after my heat circuits. I'll go up that hill to that highest level. I'm going to lose the 8 PSI, but I'm still going to have 8 PSI at my highest point. I have no ability for air to be trapped in that upper corner now and create a no heat situation where I have to go purge out a heat circuit. All that took place. We changed nothing else in the system except moving the circulator from pumping into the expansion tank to pumping away from the expansion tank. That's what fixed that system. So I know there's houses out there that you guys go to on a yearly basis and purge it out. Start looking a little deeper and try to find the root cause of why are you going to that house every year, maybe twice a year, purging out the system. This may be one of the reasons. So again, that has to do with circulator positioning. We're good, Jim?
Yes.
Yeah. Okay, we're going to jump into primary, secondary piping, and we really want to simplify this. So basically, primary, secondary piping, it's a big fancy word for a Band-Aid in my book. Basically, what we're doing here is we are controlling the flow. Here we have a, Chris, can you see this NTI boiler on there? A little out of screen. There it is. So we got an NTI boiler here, and this is a TRX. We pipe it off the bottom. This boiler needs primary, secondary. Inside this jacket, there's a Takeo e-circulator in here, and that e-circulator's responsibility is to make sure we flow water across this heat exchanger at all times. So for primary, secondary, we need 2 closely spaced T's. And what those closely spaced T's do is 4 to 8 pipe diameters, outside dimension to outside dimension. What that does is it allows us to manipulate the water between those 2 closely spaced T's. And so water can sit still, water can flow through, or water can actually flow in a reverse flow through the closely spaced T's. It gives us the ability, because of the low pressure drop, to manipulate the water between those 2 T's. So this is an existing boiler system. We're going to go in there, we're going to find somewhere on the supply, somewhere on the return, and we're going to cut those pipes. remove the old boiler. That was the easiest boiler removal you'll ever have. And we're going to take and slide in a couple new ones. We're going to do a multiple boiler system here. We just took the supply and the header, supply header right here, and the return header. We tied them together. And somewhere along that run of tying those two together, we put in closely spaced T's with the bowl of the T going to the boilers. And here we have 4 boilers. We're going to just tuck them into the supply in a reverse return pattern. So first in, last out. Okay, first in. The return on this would be last out. And this right here is a hydraulic separation point. So the circulator that's going to be mounted here on the boilers will not see this base mount circulator in the system, and vice versa. That's why we do primary, secondary T's, is to hydraulically separate the two systems. This is what it would look like after it's piped in. And again, we would have reverse return. So here's this boiler here is going to be third in to the supply side, and it's going to be first out. That will guarantee that all boilers do the same work and that all boilers have relatively the same temperature across them. We're not going to have one boiler heating the other boiler and the other boiler heating the third boiler, and just makes for an inefficient system. So here we have a primary secondary system. This is the spot of my closely spaced T's. Right here is a boiler. It says here I have 14 gallons per minute going across that boiler. You go back to your universal hydronic formula, figure a 20-degree delta T, 20 times 500, right, the weight of water, equals 10,000. 10,000 times 14, this is 140,000 BTU boiler, okay? This circulator probably came with the boiler. Its only function in life is to make sure we have water flowing across this boiler's heat exchanger. That's all it cares about. This circulator, because of my closely spaced T's, does not see this circulator, or the circulator. So in this scenario, the boiler's telling us it needs 14 gallons per minute. That's what it's telling us. This circulator is going to supply 14 gallons a minute to that heat exchanger. So I have a demand. Each circulator up here has the ability to move 7 gallons per minute. One circulator is on. What's my flow rate right here? This is where we're going to get quick with our hands typing. If somebody could type into Jim what my flow rate is here. Okay. So I'm looking for 3. Okay. So if he has 3 correct answers, he'll give it a nod and I can keep going. So this really starts the interactive part. So figure out where that little question box is over there and message box, and start typing.
All right, we got 2 answers. Richard says 7. Daniel says 14.
Okay, so one circulator is on. The answer right there is going to be 7. So this circulator is looking for 7 gallons of flow here. And we have 7 gallons of flow going out to the system, which means it's going to go out. It's going to give up its energy out here in spaceport circuit, let's call it, back to Jim's diagram in week 2. And that 7 gallons will come back here. We used up some of the energy in it. It's going to get to this point, and what's going to happen at this point? $7 gallons in our return header. Boiler is looking for 14 gallons. This boiler is going to get its 14 gallons because this circulator says so. I'm going to take 7 gallons coming from the return. I have 14 gallons coming through my boiler, back up and out. I get to this point, that water makes a decision. The system is looking for 7. 7 will go that way. The boiler is looking for 14. 7 is going to go this way. It's going to mix with the 7 coming this way, and it will deliver 14 gallons of flow to that heat exchanger. Who can tell me how that boiler, condensing modulating boiler, how it will react right now based upon 7 gallons of heated water, 7 gallons of partially heated water, use some of it through the baseboard, combining right there, and then going 14 gallons into the boiler. How's that condensing modulating boiler going to react? This is a little easier when we're all in the room together, guys. So I keep looking over to Jim for, seeing what guys are firing in his answers.
We got two.
Got 2 answers coming in. What do you got?
We got the capacity's gonna ramp.
Okay, great answer. The capacity will ramp down. Why will it ramp down? Because we're taking, and I'm gonna use a crazy number here. I know I said condensing boiler, but everybody's comfortable with 160, 180. I have 180 degree water, 7 gallons of it. It's gonna come backwards. I'm gonna call this 160. They're gonna mix and they're gonna drop back into the boiler at potentially 170 degrees. I have a return water sensor that's gonna recognize that, and it's gonna tell my boiler input to reduce itself because my delta T of my heat exchanger is only 10 degrees. So the boiler has no idea how many heat circuits are falling. It only knows that the return water temperature is pretty warm and the water leaving the boiler is right on target. And it says, I'm pretty comfortable here. I can start to reduce the input. I'm still going to satisfy the demand that I'm currently receiving, right? So the first thing that can happen between those two closely spaced T's, and there's no order for second or third, this is just the way we're presenting it, is in this scenario with only one circulator on for heat, water will actually go in a reverse flow to support the water that the boiler needs, keep the heat exchanger cooled properly. Scenario number 1, go.
Just a question that came in, and it reverts back to when we had multiple boilers, primary, secondary.
Yep.
At the boiler, does piping length matter if there's more elbows,
Yes.
say on one boiler versus the other 2 or 3?
Great question. So majority of the boiler manufacturers, depending on the size of the boiler, they'll give you somewhere between 10 and 20 equivalent feet worth of pipe that can be attached. So including your elbows and your length of pipe, linear feet of pipe, they'll give you about 20 feet, 10 to 20 feet from the boiler connection point to the bowl of the T's going into your primary, secondary T's. So hopefully that'll answer that. Keep them coming. Here, it's a little cooler day outside, so now our second zone just came on. So 2 zones at 7. What's our flow rate going to be here? 14. What's our flow rate on our return? 14. What's happening between the 2 closely spaced T's right now? I hear Jim typing. So if I have 14 gallons going down to my boiler, and I have 14 gallons in my system, between those 2 closely spaced T's, 0. Nothing is going on between the 2 closely spaced T's because I have equal flow rates on both sides. Because they're closely spaced T's, we can control that pressure drop between the 2 T's, and in this scenario, no water is flowing. So that's the second thing that can happen between the 2 closely spaced T's. Now, it's even colder outside. Now we have all 3 heat circuits in the house that are on. There's 7 gallons apiece. So I now have 21 gallons of flow in my header, which gives me 21 gallons of flow on my return header. What's going on between the 2 closely spaced T's right now? And I will wait for someone to answer.
One response,
What we got?
7 GPM.
7 GPM, and that's correct. It will be in the bypass mode, and guys will respond. So keep it going, keep typing. So in this scenario, we're going to bypass water across those closely spaced T's because our system flow is greater than our boiler needs or can handle, for that matter. So this is a scenario where realistically we're over pumping. And this will get into the zone valve circulator conversation we'll have here in a little while. And again, there's no right or wrong. It's just, we're going to throw a couple things out there. This is your house. And this is, again, just for see where we are. We don't give a test, but we like to have little checkpoints in here to make sure we're delivering the message properly. So this is your house. It's a 140,000 BTU boiler. It is a design day. So wherever your design temperature is, New Jersey 14, up where I am, 0. All 3 heat circuits are on. If this was your house, you were paying for the gas that's going to be burned by this boiler. Coldest day of the year, what would you like to be going on between the 2 closest spaced T's right now? Live, right now, coldest day, design temperature outside, you're trying to keep it 70 in your house, you're paying for the gas going into that unit. What would you like to have happen between those 2 closest spaced T's right now? Firing some answers to Jim. You want backwards, reverse flow? You want no flow? Or do you want bypass?
All right, majority are saying no flow. A couple people saying there's 7 GPM, one saying 13 GPM.
Remember, I did not give you any flow rates out here in this scenario on these circulators, just to let your mind work. Okay? What I would like to see, if I'm paying for the gas in this system, I want 0 flow between those 2 closest spaced T's on a design day. And why would I say that? I'm paying for the gas going into that boiler. I'm producing BTU with that gas. I want every BTU on the coldest day of the year to be delivered to my home. I don't want any bypass going on between the 2 closest spaced T's, whether it's reverse or bypass forward, because that's going to change my delivery temperature on the coldest day of the year, the delivery temperature of that water to my baseboard. So just a little, fun fact finder to see where everybody is, as we get into this course here. All right, so got to be real quick with the fingers here. Is that primary, secondary? I'm going to say yes, it is. Who can fire off an answer? What's going on between those closely spaced T's? Tick, 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 tick.
All right, 2 for no flow.
2 for no flow.
A majority are coming in at 10 GPM.
10 GPM. There's the answer. And it's reverse flow, right? Our boiler circulator is looking for 20 GPM. It's hungry. It wants to eat. Wants to run close to 200,000 BTU across this boiler. Our system right here is only taking 10 right now. So we would have 10 gallons of reverse flow to give that boiler its 20. All right. Again, quick on the hands here. What do we got going on in this one? Is that primary, secondary? I'll say yes, it is. What's going on between the T's?
Everybody got this one.
Okay, awesome. Everybody's got that one. No flow. Great. I don't know why I put an arrow going that way, but it's no flow. Okay. I will tell you again, this is primary, secondary. What's going on between the 2 closely spaced T's? Jim's got a smile on so big right now, it's almost funny. I can't even look over there.
Yeah, they're nailing it.
They're nailing it. Good. So again, we're going to bypass 10 in this scenario. Okay, is this primary, secondary? This is a yes or no answer. Fire them answers in. Big thumbs up. Yes, it's primary, secondary. Holy cow, we can do moose antlers with primary, secondary. Yes, we can. Is this primary, secondary? This is a yes or no answer.
We're getting yes.
Okay, we're getting yes. Can anybody tell me what's wrong with this picture?
That's why I'm laughing.
Good, because they knew I was going there. Yes, you're right. If you said those red circulators are wrong with that picture, you're right, because we're the green guys. And I'm still paying for a kid to go through college, so let's keep them green. All right, good. So, is this primary, secondary?
Yes, everybody's saying yes.
Everybody's saying yes. Okay, it's primary, secondary. It's a multiple boiler application. Is it piped properly? Is it reverse return? I will put the highlighter on here and you answer, Jim, this is the supply coming out. It goes here, first in. Here's the return. It comes up, over, and here it's the last out. Does that pipe properly?
Getting a lot of yeses.
Yes, it is. Great. Okay. Is this primary, secondary? And if so, not counting the boiler connections, how many primary, secondary connections are there? Not counting where the boiler's tucked in here, how many primary, secondary connections are there? And did you even know that it's possible to do multiple primary, secondary connections in one system?
The majority, yes, they all say it's primary, secondary. We're getting answers of 4, 2, 5.
Okay, so let's go through them.
One gentleman said very old school.
Very old school, no doubt about it. Like, we're showing things. Look, I got a young mentor. I said that last week or the week before. Well, maybe I'm your old man mentor right now. So it is old school. So boilers in, reverse return, primary, secondary connection here. This becomes our hot loop. We take our hottest temperature to our indirect off first. We come around, we go to our second hottest temperature, baseboard, another primary, secondary connection. Then we go to a snow melt system through a plate exchanger, another primary, secondary connection. And this is an old injection panel, which is realistically primary, secondary. So that would theoretically be another primary, secondary circuit. So yes, it is old school. You won't see this, but we put it up there because it's out there. And, for the guys that are new in the industry, they may see this. I just want them to know what it is. Are we good on primary, secondary? Anybody has any questions?
One question that came in is, Jim is asking, is it a monoflow?
Is that a monoflow?
No.
No, that's not a monoflow. That is just closely spaced tees. Sorry about that, wrong button. Closely spaced tees. Each circuit has its own circulator with a dedicated flow. And this circulator has very little head restriction, but its goal is to support the total volume of gallons for all of the heating coming off of that hot circuit. Okay? So if we're good on primary, secondary, if you got a question, you can still fire it over there to Jim. He'll either call it out live or answer it privately. Today's zone valves, you're going to want to write this down somewhere because this will play into your root cause troubleshooting. The CV of a Honeywell zone valve, standard Honeywell zone valve is 3.5, which translates to about 35,000 BTU worth of energy we can put through that valve. The zone century, 10.3, our most common one, that's the sweat valve. Our most common one, which is the press valve, about 9.5, so about 95,000 BTU through a 3/4 press zone century. Okay, just write that down. That's going to be important later on, just because it's a BTU thing, right? The amp draw, Jim will touch on this more next week. I'm just going to fly through it today because I want to get into more root cause troubleshooting. Now I'm going to ask the question, how many guys are zone valve guys? How many guys are circulator guys? And if you can, just throw an answer in there, why? And then we'll go the next step. You a single circulator with multiple zone centuries, or are you a straight up zone valve or a circulator guy? You want circulators on there because getting any answers?
I've got, 50-50. Search for redundancy, zone valves, both. Depends on the job.
I like that answer.
It doesn't matter as long as it's green. We're hugging.
Yeah, we are. Yeah. So I really like the one answer there. It said, This just said click here to unmute my microphone. I go, can you hear me? Oh, you can, okay. I got a pop up on the screen, sorry, everyone. So what's happening here is we're gonna take and throw this up there. And I understand circulators because you want the redundancy. If this circulator were to fail, I would still have heat in half of my home with this two circulator job. Here, I have a 2 zone valve job. If this circulator were to fail, I have no heat in both zones. We understand that. The technology in these zone valves has gotten so much better than it was even 5 years ago, 6 years ago. They're pretty robust. So what we like to do, and this is just a talking point, just to get you thinking, is right around that 130,000 BTU worth of input and under. I lean personally, and this is personal preference, that's it. I lean towards a zone valve job under that 130,000 BTU worth of input, so call it that 110 net range, in that range. And if it's over 130,000 BTU, I'll lean more towards a circulator type job. And the gentleman who said it depends, it does depend. And the reason, I'm going to give you the reasons why I would go that route. The capacity of the circulator that potentially comes with your boiler, and the 007E has become extremely popular on new boilers. It's got a capacity. And I'm just going to go to the next chart to show you the capacity. So at 10 feet of head, this 007E gets us out here at about 82,500 BTU. If I want to get all the way out to that 120-ish range, I'm limited to about 5.5 feet of head. So again, the reason I kind of, in my head, think that 130 range is the range where I would look at a system as being a zone valve job or being a circulator job above 130. That job I showed you a little earlier, where we were over pumping, if I take a 80,000 BTU boiler and I put 4 circulators on there, I know I'm over pumping that system. Even with 3 circulators, I'm going to over pump what that boiler is capable of. So this is just a reference point. Again, there's no right or wrong answer. This is going to be a preference, and it really, to get the right compliance into the application, we just throw some numbers at it for you. So here, these are circulator charts. Again, in your TACO catalog, which you have, we're going, next we're starting the root cause troubleshooting here. So 44, 48, 50, 52 are the pages that you're going to be looking for in your catalog. And we're going to get started right here. The first problem we're going to do is we're going to deal with page 44. So in this scenario, you walk in, you have a job site, you're trying to figure out what's going on within the heat circuit, figure out if your circulator is sized correctly. So you have a 20,000 BTU zone. So you have 20,000 BTU worth of baseboard on there. That would require, using the universal hydronic formula, you can work this backwards, that will require 2 gallons per minute of flow. You have 40 feet of baseboard and 125 feet of pipe and fittings. So that would give you a total equivalent length of 165. So with that 165, I would like you to calculate the head loss of that heat circuit and just fire those answers into Jim, please. Use your head loss calculation on page 44 in your TACO handout that was shipped out to you guys. You get answers?
Not yet.
Okay, so I'm going to write the formula on the board. So the total equivalent length, I have 165. If I go into my catalog on page 44, it tells me to multiply that by 1.5 tells me to multiply that by 0.04. That will give me the head loss of that heat circuit. Has anyone fired in an answer?
2 answers, both the same.
And they should be 9.9.
On the button.
Okay. Just take a second. Run that math. Because we're going to be doing this. This is going to be part of what we're doing here for the rest of the class today. Okay, so that's page 44. It says head loss for copper pipe. Measure the length of the run. Multiply that by 1.5. That's going to give you a 50% fudge factor for valves and fittings. Then you're going to multiply that by 0.04. That will be for every 100 feet, give you proper velocity. Okay, so next one up. Get your calculators ready again. We did this last week. No, 2 weeks ago. Jim did last week, sorry. So here we're going to figure out the recovery time of this system. So right there it shows you have a 100,000 BTU boiler. You have a Honeywell 3/4 zone valve feeding your indirect. So in this formula, the tank holds 36 gallons per minute of water, or 36 gallons of water. Our supply temperature is 115. Our inlet water temperature is 50. That equals 65. 115 subtract 50 is 65. Here's that 500. That's the weight of water, right? That's a pretty standard number in our formulas. So I'm going to do 36 times 65 times 500. And what am I dividing that by? Am I dividing it by the size of this boiler? Or am I dividing it by the size of this roadblock to support the heat needed to make hot water? Someone tell me how long it will take that system right there. You will see in someone's house within the next 3 days if you're in basements. Tell me how long it will take to heat that indirect back up, recover the water in that indirect. We're losing everybody, Jim.
A little confusion out there, yeah.
Okay. So it's 36 times 65 times 500. About 4 slides ago, I said write down a BTU value. Let's BTU value, Honeywell zone valve, 3.5 CV equal to approximately 35,000 BTU. Here's your formula. My restriction point is that zone valve at 35,000 BTU. How long will it take to recover that indirect?
Okay, now they're coming in. 33 minutes to change. If that math is right.
33.4 minutes. So what is the scenario here? You got called into that house. The homeowner is complaining of insufficient hot water. If you see a system like this, you could have a 1,000,000 BTU boiler there. It does not matter. What matters is, what is my piping size? What is my method of supporting the water to the indirect? What does all that look like? Okay, well, we know that that 35,000 BTU roadblock is right there. I have 100,000 BTU here. I can have inch and a quarter piping here, 3/4 Honeywell zone valve roadblock, 35,000 BTU going to my indirect. That's it. I can't change that. That's physics. I mean, that's the recovery time. So I go back like, when we're training live here, I had a guy right in the front row, and I know him for quite a while. And he went home and did the math on his, and he came back with almost the same exact scenario. And he figured out why he has insufficient hot water, and he was going to fix it. Easy fix, put his own Sentry in there, and you'll get the 95,000 BTU worth of energy going over to that indirect. Okay, so here we go. We're moving on. So,
Oh, John,
yes, sir.
so just a question came up randomly, but what would be a good recovery time? What would be something that we would shoot for?
Most indirects, if piped properly and pumped properly, you're probably in that 11 to 13 minute range. If I have the correct, 40 gallon, a typical 40 gallon indirect will absorb about 150,000 BTU depending on the brand. So if I'm driving it to full capacity and I'm going to support that first hour delivery and recovery and everything, yeah, somewhere in that 11 to 13 minute range should be really good. Okay, this scenario, here's a boiler room. And really right now, this is just going to be a fact checking boiler room. I'm not going to give you a service call here. This is more of a fact checking. Again, I need to know where you guys are to make sure that you can continue forward with root cause troubleshooting. Because there's more this week, there's more next week. The space heating load for this job is 100,000 BTU. All right, so I have 4 heat zones up here, pulling 25,000 BTU each. 4 zone valves, 25,000 BTU each. That's 100,000 BTU. The domestic hot water tank right here, this coil in this tank can absorb 120,000 BTU. You're going to pick a boiler size. That's up to you. 100, 120, doesn't matter to me. That's up to you. Your longest heat circuit is 135 feet. So you're going to use your TEL. There's one example on the board right now. You can just rework the numbers. Your largest zone out here, I said 425,000. Your largest zone out here is 40,000 BTU. This boiler heat exchanger, this is a water tube heat exchanger. It has a 12 feet head drop. So there's the head of the boiler. The head drop of this indirect is also 12 feet. What I'd like you to do is figure out P1 and figure out P2. I want you to calculate those circulators. What size would those circulators be to overcome the 12 feet of head of the boiler at the correct flow rate and the 12 feet of head at your indirect at the correct flow rate? And just run through the exercise. We'll take your 135 and you're going to do the same math as we have here, except this is going to be 135 and see where you land. While you're doing that, I'll make the changes to this. For your circulator chart, figure this out, you'll probably be using page 52. If anyone needs a circulator chart on the screen, I can click through and get you a circulator chart if need be. Just let Jim know.
It must be working.
Oh, they're working, yeah, this is a headache week 3.
Please put up the chart, yes.
Okay, everybody has the information they need off of here. So we will go to a chart that will work for you, and it would look like that. Or it would look like that. They're not even in the room with us, and I can tell how silent it is right now. Usually when we're live, it goes real quiet right about now. So I think the same thing is going on even though we're not live.
Just an FYI for you, one gentleman did pick 120,000.
That's fine.
Just to
Yeah,
let you know.
okay, good, all right, good.
Somebody's.
Yep, that's good. Okay. No one has asked the question, but we are going to assume a 20-degree delta T. Again, I don't put that out there. I just want to see if the questions come in or where you guys are. I'm going to think that you're at a 20-degree delta.
I'm sorry, we're picking P1 and 2?
P1 and P2.
Okay.
And once they figure out flow and head, which they have the head for both of them, the flow is going to be based on their boiler size. It becomes redundant.
One gentleman asked if you could put the problem back on the screen.
Yes, we can. I like it.
We're getting answers, but they're only picking one pump.
Okay. The 12, which pump do they pick? P1 or P2?
It looks like they're picking P1.
P1, are they picking it as a 0012?
No.
Okay. So for the gentlemen that have picked and ladies that have picked P1, here is P1. So I always like to look at a diagram like this, and I look at P1 and I say, what work does P1 have to do, right? Because that's what a circulator is. It's going to perform work. Its job is to move water. Its job is to overcome the restriction of the heat exchanger, which in this scenario, I gave you the answer is 12 feet of head. So Jim told me that someone picked a 120,000 BTU boiler. So if I go to that universal hydronic formula and I have a 120,000 BTU boiler, Jim told you the shortcut. Move the comma over one position. That means I need 12 gallons of flow. 12 gallons of flow has, with that circulator P1, also has to overcome 12 feet of head restriction. So I'm going to just fast forward here, and I'm going to get right here, and I am going to go 12 feet of head, come across until I get right there, straight down, 12 GPM, 12 feet of head. I am right below line number 10. I go over here to line number 10. It's a 0012, right? So for P1, I would need a 0012. I have to overcome 12 feet of head, and this was a 120,000 BTU boiler. Even if it was a 100,000 BTU boiler, it's 10 GPM. For my indirect, it's 12 feet of head. And I'll go to that chart again. And it could be, here's 12 feet of head. It could be 10 or 12 GPM. I'll go right up in between them, and I will land right there. And I will still be under line number 10. So both circulators would be a 0010. Or if I want to do a more efficient circulator, if I go to 12 feet of head, out here to 12 GPM, I could use a 006 or 0026 E circulator, and I would put it on medium speed, and I would fall right in that category right there. So I think we had a couple of guys struggle on that one. We will move to the next one. Jim is typing away. He's gonna have sore fingers by the end of the day. All right, next scenario. I'm gonna throw you a curveball here. In this scenario, we have a condensing modulating boiler. That boiler has 8 feet of head. So the restriction, the head loss across the boiler is 8 feet. It's a 120,000 BTU boiler. On the boiler circuit, we have a low loss header here, so we have primary, secondary. Okay? On the boiler loop, we're gonna go with a 30-degree delta T. So you're gonna need that universal hydronic formula and figure out your 30-degree delta. On the boiler side, after you figure that out, you'll know the pipe size. You'll give us the flow rate. And if you want to go further, you can even figure out the circulator. That's what you're going to tell us on the boiler side. These are fact-finding missions. Why is the system not working properly? Out here on the system side, we have 3 heat circuits. Each heat circuit is 40,000 BTU, and the longest heat circuit is 135 feet. So remember, 20-degree delta T out here, take the comma, move it over one position, you'll know your flow rate. So size the circulator for here, you're gonna need your total equivalent length for the here, and on the boiler side, 30-degree delta, pipe size, flow rate, circulator size. And if you got questions, fire them in. I have capacity charts for piping and circulator charts here if you need them. Let Jim know and I'll bounce between all the different charts for you. I'll give it the answers away.
They are definitely working.
Yeah, I can hear them. I went through a ruler about 2 seconds ago across the room. Anytime you're in a boiler room, try to keep yourself from going down a wrong path or getting off on a tangent. Always do what you know first when you're trying to problem solve. If you know how to do the universal hydronic formula, we'll start there. So that's page 44 in your take-home catalog that we sent you. So if I were to take the universal hydronic formula, I do not know the flow rate. I know the BTUH, that's 120, right? My delta T is 30. So 30 times 500 is going to be 15,000. So take your 15,000, divide it into your BTUH, and that'll give you your flow rate. And then you can start to size piping and head on down the line. So universal hydronic formula is always a good go-to, and start to figure it out with that, and then let the problem start to come to you a little bit.
A couple of answers coming in.
Okay, Jim's getting some answers in. What portion are you getting answers in on?
Couple on pipe size, 1 inch or 1.25 inches.
Okay, so let's go to, I'll just flip one slide forward. So we got 120,000 BTU comfortably through 1 inch pipe with a 20-degree delta T. I could move 80, but remember the boiler size is at 30-degree delta T, right? So 1 inch pipe would be the correct answer, because here at a 30-degree delta T, we can comfortably move that through 1 inch pipe. So on the boiler side, 1-inch pipe is correct. Do we have a flow rate?
One response on the flow rate,
And what'd you get?
8 GPM.
8 GPM on the flow rate is also correct. Do we have anyone attempting the circulator size on the boiler loop?
One response,
And it is
a 007.
007 will probably be a little light there. But if you went with a 007E, because of that 10 feet of pennant, that'll get you your 8 and 8, no problem.
One gentleman went with a 0012.
Yeah, that's a big boy. You're paying up for that.
We have another gentleman, one of our friends, 0026E.
0026E will also work there, yes. Yep. That would work. But 7 will do it too. 7's close. 7, 15, E3. They'll all work for that boiler side. All right.
One question came in on the system side.
Yep.
The question was, is each zone 40,000 BTUs?
Nope, we have 3 zones. Yes, 3 zones are 40,000 BTU each. So 3 times 4 is 12, 120,000 BTU boiler, 120,000 BTU going out to that system. So again, do what you know first. You know now your flow rate, calculate your TEL, and then you can size the circulator for the system side. Be quiet out there.
One question came in that you probably want to touch on, or a comment. So on condensing boilers, should we use a 30-degree delta?
So I'll answer that in 1 second. We'll wrap up this problem solving and then we'll touch on why I did this the way I did this and why we have 2 different deltas running the system. And is that even possible?
So a couple answers on the system pump.
Yep.
0010.
Yep. I like a 0010, 0010, 0026E. If anybody gets real adventurous and they want a temperature control, BT2218 will also work on that side. So there's the circulators. We'll just walk through this. So I always say do what you know first. 30-degree delta, go back to that universal hydronic formula, calculate it out. Every gallon of water has the ability to absorb and deliver 15,000 BTU. So we go to our pipe chart. That will allow us with a 30-degree delta. On our pipe chart, we showed you that. That'll allow us to get you a 30-degree delta with 1-inch pipe, and we'll flow that comfortably. We go through 1-inch pipe, circulator size, everything there is good on the other end. So the question was, do we want to do a 30-degree delta T on a condensing boiler? And it's not going to hurt a condensing boiler to have a 30-degree delta. It may make it condense more, which will make it more efficient. But in addition to that, on this condensing boiler, I was able to allow you to go from an 1.25 header and 4,900 air separator and other items at a 20-degree delta T. You would have had to have 1.25 piping on all of that. So there was actually a cost savings for you, the installer, to do that in 1 inch with a 30-degree delta on a condensing piece of equipment. And then we'll control the flow and everything else going on over there in our system to try to keep that at a 20-degree delta. Another reason that BT2218 would be really nice on that heating side. So these are fact-finding missions. We do this daily with contractors, where there's a potential problem on a job site and they, we have to end up on a job with them and we'll go through, we're going to do exactly what we just did live in the basement to see where we may see a problem within that system and correct it and be confident when we go to correct it, because we've done a little bit of math to figure out exactly what that system is telling us it needs. All right? So, any other questions on that problem?
Actually, two good questions.
Go.
One's gonna take you down a different road, but it's a good one. Number one, why would you have an air separator and a hydro separator? The second question is, what's the best way for a technician to look at a new system to see if the designer designed it for a 20-degree delta or a 30-degree delta?
Right, so on the system side, we'll start on the system side. Basically, whatever it's connected to is really what's gonna dictate the delta, right? So if it's a baseboard system, we know it's a 20-degree delta, and we'll calculate that there. On the boiler side, if it's a cast iron boiler, it should be a 20-degree delta. If it's a condensing boiler, it could be anywhere from, 20 to 35. The problem is, we're really only going to see those temperatures on a design day. So majority of the time, those deltas are going to be lower than what they will be on design day. And as we talked about last week, 3% of your heating season, you're running at design conditions. So you don't have a big opportunity to see that. And that's a hydro separator with an air can on the top. It's more of a hydro separator than an air separator on that system. So there's a bunch of different ones made that are out there. That looks like the Takeo version. It's basically just a copper diameter pipe, has the air separation on top, and then has your closely spaced T's coming into the sides of it, and then it has a drain on the bottom. So that's more of a hydraulic separator. The air separator that's on the boiler side is going to take care of any of the air that might be in the boiler or work its way back to the system. Any of the system air may get caught in the hydro separator and eliminate it there. In this photo, they're just using it for hydraulic separation. Okay. This next one is going to require some work. We went through and we did all the head loss calculations. So basically, from circuit 1 through 7, we have measured all of the heat circuits. And we multiplied them by 1.5, multiplied that by 0.04, and we came up with the head loss of each one of the heat circuits. We're also kind enough in this example, as a time saver, we gave you the flow rate for each one of those heat circuits. So what your job is now is to take heat circuit 1 with flow rate 1, head and flow, and calculate what the circulator should be for 1, 2, 3, 4, 5, 6, and 7. And then we would like to know the size of the header to support the BTU of this system, and this circulator size to move the water across this cast iron boiler and get the proper flow. So I will put up a circulator chart whenever you need it. I'll flip back and forth between this problem and a circulator chart, but that's what you are tasked with right now. We are trying to figure out why this homeowner is complaining, and we want to make sure that all of these circulators are sized correctly, and that the boiler piping header is sized correctly, and that the boiler circulator is correct to deliver the proper BTU to the home. So you can start working. If you have questions, please fire them in. We're probably going to be working on this one for probably a good 5+ minutes. So dive in here, go through the exercise. It's worth it. You will use your universal hydronic formula. You will use your pipe sizing chart. You will use your circulator sizing charts to solve the concerns of this homeowner. And I am waiting for one question from the field about this scenario. There's one question you have to ask us in order to figure out this problem or the potential problem.
All right, so 3 people have asked what size is the boiler?
Universal hydronic formula will size the boiler. There's another question that they need to ask in order to give us all the answers we're looking for here.
All right, one guy's got the question.
Okay, what is it?
What's the delta T?
Delta T is going to be 20. Still not the right question. That's a great question. There's still one more. No.
You got a bunch of people focusing on what's the longest run.
Don't worry about that. We took care of that for you. We gave you the head loss. Don't worry about the longest run. But you are sizing circulators. Hint, hint. Somebody real quickly, fire off to Jim. What are the 2 things you need to size a circulator? I always do it like this, right? Blank and blank.
Elaine's got it.
I do. I do. I'll answer.
One gentleman does have the boiler our size.
Okay. I'll get that in 1 second. Still don't have the question needed. Finish this problem.
Oh. My bad.
We'll go about another minute and then start taking some answers that Jim is receiving and start throwing them up on the board here and see what we end up with.
I'm trying to think, but nothing happens.
So one gentleman is asking, are you asking what else we need besides circs?
Not the system circs, but I did ask for a boiler circulator size. What do you need to size that?
Wow, we have one high achiever going for a boiler circ based on a 35-degree delta.
On a cast iron?
That's where he's going.
Must be a big commercial application. That's deep.
All right, so Richard has that question.
Okay.
What's the head loss?
Okay, that's the one we're looking for. In order to size that boiler circulator, you would need to know the head loss of the boiler because we did not give you that. That's the one thing we did not give you here. typically cast iron boilers in general will fall somewhere in the 2 to 3 feet of head loss. So you can go 2 feet of head loss on this job because very short piping. Yeah, 2 feet of head loss will go with at your flow rate, whatever it is. That's you have to figure out the flow rate.
Two people have gotten the boiler flow rate, actually three.
Okay, so good. All right, we're gonna go. We got one more problem we need to solve before we're done. I hope everybody's having a little bit of fun with this and not getting too aggravated with this. But so what do we know? Well, we gave you the flow rate of each heat circuit, right? So here's the universal hydronic formula. And anytime we use the universal hydronic formula, if we know 2 of the 3 things, we can always figure out the third, right? So we know it's a cast iron boiler. Cast iron boiler lives with a 20-degree delta T. So 20 times 500 equals 10,000, right? Does that start to sound familiar? Here's our boiler. Do we know our boiler size currently? No, we don't. But with that problem that we gave you the flow rates. Zone 1, 3.5. Zone 2, 3.5. Zone 3, 3 gallons. Zone 4, 4 gallons. Zone 5, 2.5. Zone 6, 4.5. And zone 7, 6 gallons. Do we know the gallons per minute? Yes, we do. That is 27. So if I know I have 27 gallons of flow, I'm going to multiply that by 10,000 to give me a boiler size of 270,000 BTU, which is right there. We just figured out the one that we did not know. So now that we know the boiler size, we can now size the circulator, which is going to be 27 GPM at 2 feet of head. And what did we get for a circulator, Jim?
A bunch of people coming in at 0010s.
For the boiler?
Yeah.
I like it. 0010 or 0026E. If you want to go high efficiency. Okay? Now, what size pipe do I need to support this capacity of the boiler? If anybody needs that pipe chart, I can pop it back up there.
We had 2 answers,
You did. What do you got?
2 inch.
Okay, so that'd be 2-inch copper. And I'll be a good guy and I'll even take 1.5 iron, which is right on the edge. Okay, so we solved everything on the boiler side. Now let's talk about them zones 1 through 7. Zone 1 and 2, fire off a circulator you came up with for zones 1 and 2. What size circulator would it be? What are you seeing?
One gentleman went deep into the 00 chart, 005.
Yeah, 005, 006B. Zone 3, 005. Zone 4, what do you got for zone 4? It'll be another 006. Let's go down to zone 6. Tell me what you get for zone 6.
One gentleman went for 0010.
He's right. 0010. So when I do all these, I have 2 006Bs, bronze, because it fits that curve, 1 005, a 006, another 006, a 0010. potentially a 007 or a 0010 on zone 7. I could simplify that job, put 0015 E3s on there and have them set to low or medium and meet the exact flow rates of each one of those heat circuits. Because I know no one has ever installed a 006 as a heating circulator. It's rare if you've ever installed a 005 as a heating circulator. And the cost of a 0010 for a heat circulator, it adds up. So we could take an E circulator, a 007 would cover all these, a 0015 would cover them all, and you'd be able to dial it into the correct flow rate. So thinking outside the box a little bit, just looking at a job like this where we have all different flow rates and all different head pressures. An E circulator gives you a really nice wide window to operate within. Jim, any questions we have to hit on this loose antler job before we move on?
No, sir.
Okay. This will be the last root cause troubleshoot problem of the day. It's 8:31. So just bear with us for like another 3 or 4 minutes and we'll get this out of the way. So here we have a typical boiler with an air handler. And we have a radiant circuit out here. So the BTU of this air handler is 48,000 BTU. This coil has a 8-foot head drop. This run to and from that air handler is 25 feet. The delta T of the air handler system is 20 degrees. Can you give me the flow rate, the pipe size, and the circulator size for the air handler? And then out here in the radiant circuit, we give you the head drop of 12 feet of head drop for this radiant system. It is a 33,000 BTU slab. We're going to do a 10-degree delta T. I'd like to get the flow rate and the pipe size feeding this radiant manifold. If you have any questions for us, please ask. And I will make some changes to the board to get prepared for this scenario. Cast iron boiler, just in case anyone wants to know. Very low head drop too. You will deal with something here, we'll call it a cumulative head pressure. And you'll deal with that on the air handler side. Got some stuff coming in.
The gentleman who's he's got the GPM,
Okay,
got the pipe size,
okay,
he picked the circulator.
okay. I like it. Again, do what you know first. So we got a 20-degree delta T. The flow rate should jump right out at everybody. What'd you get for a flow rate, Jim?
4.8.
4.8, so that's spot on. Head pressure, we got 8 feet of head drop through the air handler. Got 25 feet out and back. So the 25 feet, 25 times 1.5 times 0.04 equals 1.5. So 1.5 plus the 8 feet of head will give you 9.5 feet of head. You need that to figure your circulator. So based on 9.5 and 4.8. What circulator did we come up with?
Well, Jen said a 007 as the minimum.
007. I'll take a 007E. I'll take a 0010.
Yep, I just cleaned it.
I like the 0010 better than the standard 007 in that application. And I like a 0015 E3 on high. The 0015 E3 is a pretty universal circulator. Okay, so on the air handler side, while guys are still working on the radiant side, on the air handler side, the potential call here while you're on that job, while you're calculating this out, is insufficient heat at or near design day. Did anyone throw us a pipe size for that air handler?
1 inch.
1 inch. How many times do you go to an air handler like this and it's piped with 3/4 inch pipe, which really only carries about 40,000 BTU. So on near or design day, you could have short cycling of the blower because we're losing temperature too quickly, because we're not delivering the BTU to the air handler that's needed, which would be a insufficient heat call. So this is why we're going through these exercises, so you can apply this to the real world when you're in someone's home and they have an insufficient heat call. You can find the root cause of that insufficient heat call.
One of our friends said, well, we see 3/4 packs as the pipe size.
That's true.
That is true
Very true.
and painful.
Yeah, that's a tough fix. There's no fix. Anybody give you any information on the radiant side?
Not yet.
Okay. So work that radiant side. On the radiant side, what do you know? We know this, right? It doesn't always have to be a boiler size. Okay? We know that. Do we know the flow rate? We don't know that yet. Do we know the delta T? Yes, we do. So every gallon of water now has the ability to carry 5,000 BTU. So what do we do here? Divide that out, tell me what my flow rate is. You don't need to, you say it like that. I'm going right back up there. You get the flow rate?
Not yet.
Out of those three things, always try to figure out what you know and what you don't know, and that will give you the third one.
Right, interesting. One gentleman nailed it 6.6, another one came in at 3.3.
He did a 20-degree delta T, right? If he did a 20-degree delta T, you move your comma over, it would be 3.3. Where we threw the curveball here, and we threw a 30-degree curveball at you today, we threw a 10-degree curveball at you at the end of the class. We're not doing this to be wise guys. We're doing this because that's real world. And we want you to be knowledgeable. We want you to be flexible. We want you to understand how to utilize this universal hydronic formula to apply it to the job that you're currently on. So 10-degree delta T times 500, 5,000. 5,000 divided into 33,000 gives us a flow rate of 6.6. To support 6.6 gallons of flow, what size pipe do we need?
Everybody's getting 1 inch.
1 inch pipe, okay? And what else are we missing here? How are we moving that water? What are we going to use to move that water? What do I need to size that circulator? We need two things. Blank and blank.
So one gentleman wants the head loss, another one wants to know the length of the run.
Head loss is right on the problem. Open up the problem. The head loss of this system is 12 feet of head loss. Got smoke coming out of your computer there, Jim? These guys are thinking that hard?
They're thinking hard.
Good, good. We're gonna let them off. I got 2 more problems here today we're not gonna get to, so. One-inch pipe, 12 feet ahead, 6.6 gallons per minute. What is that? Sorry, I think everybody just jumped off.
No.
They heard it, they checked out on it.
No. We got 0012,
That's large.
008, or 0015E3.
There we go. I like the 008. That's right on the edge. I really like the 0015 again. It's a super flexible. One of those 2 fits that bill.
That's the majority of the answers.
Awesome. That's awesome. Great. So today, today is like, it's not real world because you're obviously not in someone's basement and not breathing over your shoulder, asking you to fix the problem. But today is really a reality check as to what you really know. And no one's judging anyone here. We run this course because we want you to leave here with more than what you came with. So if you need to download that whole book, if you need to do some practice, if you need to ask questions, please don't hesitate. We said this in week 1. We want you to leave here with what you came for. And we don't necessarily know exactly what that is. Only you know what that is. So you have to be honest with yourself. Did you get through this? Did you struggle with this? Where do you need the help? Keep asking questions. Jim's there right now. I'll be there in that seat next week. We will answer the questions that you have. Again, we want to empower you with this information so you can go out there and solve problems. So we did run almost 15 minutes late. We appreciate everyone sticking with us. Stay close to the HVAC Insiders website. That's where all of our training videos go. So HVAC Insiders with the S.com. That's our media page, basically. So again, I won't hold you up any longer. Thank you, everyone, for participating. We really enjoy the engagement here. It's difficult not being face-to-face. We're trying to do the best we can with what we have. So thank you very much, everyone. We'll see you here next week at 7 a.m. It'll be week 4. We look forward to it. Have a good rest of your day. Thank you.